This is a presentation by Group 1 on the application of the first law of thermodynamics in internal combustion engines. That is a chemical engineering approach. So let's get into it. It is open on the left hand side. Compressing. So now let's dive into the introduction of the first law of thermodynamics. So the introduction to the first law of thermodynamics, as we know, states that energy can neither be created nor destroyed, but only transformed or transferred between two systems. These principles govern all thermodynamic processes, ensuring that energy is conserved within a system. Though it may change form mathematically, it is expressed as the change in internal energy is equal to heat added to the system minus work done by the system. So as you can see, I have a diagram of, I think, water in a closed container or a tight lid. So this is a closed system because, as you can see, a closed system is any system that exchanges only heat between its boundary and its surrounding. It cannot transfer mass but only energy, that's heat. So as you can see, I have a container with a closed lid and you can see the vapor coming out. That's the heat energy being lost by the system. So where the change in internal energy of this system is equal to the heat added to the system minus the work done by the system. And we know that the work done by any system is equal to the pressure times the change in volume. So that's what my diagram is illustrating. Now, this fundamental law applies to all thermodynamic systems, including internal combustion engines, as my presentation is about. In an internal combustion engine, chemical energy stored in fuel undergoes combustion, converting it into thermal energy, which is subsequently transformed into mechanical work. Understanding this law helps engineers to optimize energy conversion processes, minimizing loss and improving efficiency. This principle also extends beyond engines to refrigeration cycles, power plants, and various energy systems where heat and work interact here. Now, let's move to the next slide. Internal combustion engine. So this is an overview of an internal combustion engine. So now, as you can see from my diagram, you have a piston, we have a cylinder, and we have the gas. You see, as you can see, the system is moving up and down to burn the gas in the cylinder. Yeah. Now, the next thing is thermodynamic processes in internal combustion engines. That's the processes that goes on in an internal combustion engine. So an internal combustion engine, as I said earlier, converts chemical energy into mechanical work through combustion inside a cylinder, and it operates in a cyclic process, typically using a 4-stroke cycle. So one is the intake stroke. So let me talk a bit on what the intake stroke does. So the intake valve opens and the piston moves down, allowing a full air mixture, like example petrol or maybe air, to enter the cylinder. The pressure remains nearly constant as the volume increases. Now, the compression stroke. So the compression stroke undergoes an adiabatic process. Adiabatic process means no heat exchange. So the intake valve closes and the piston moves up, compressing the air-fuel mixture from the word compression stroke. The pressure and the temperature rises significantly due to compression. So this is what the compression stroke does. Now the power stroke. The power stroke, that is constant volume heat addition and adiabatic expansion. So now in the power stroke, a couple of things go on there. That's the spark ignition. Yeah. So that's the power stroke. A plug ignites the compressed mixture. And the last one is the exhaust stroke. And in the exhaust stroke, an isobaric process, that's constant pressure process, occurs there. So in the exhaust stroke, the exhaust valve opens and the piston moves up, pushing out the burnt gas. The cycle repeats as the intake stroke begins again. So it's like a cycle. It will go over and over and over again. So now the first law in the internal combustion cycle. So during the engine cycle, the first of thermodynamics explain how energy is transformed at each stroke. So one, at the intake stroke, heat energy is absorbed into the system as the air-fuel mixture enters. That enters the cylinder. And two, compression stroke, work is done on the gas, increasing its internal energy, that's into bracket temperature and pressure. Now, the power stroke, heat from combustion is converted into work, driving the piston down. Now, the exhaust stroke, energy is lost as exhaust gases that exits the cylinder. That's how come sometimes if you see some of these vehicles, you'll be seeing some exhaust coming out. It's because of this thermodynamic process occurring in the ICs. Yeah. Now, energy conversion in the IC. So first, in an IC, the total energy entering the system, that's the fuel, must equal the energy leaving the system, that's work and heat losses. So the energy balance equation gives Q fuel is equal to Q engine plus Q loss, where Q fuel is heat from the combustion, Q engine is work done by the gas, and Q loss is energy lost through exhaust or friction. So this equation follows the first law of thermodynamics, ensuring energy conservation in the system. So heat transfer in the IC. So now a four-stroke engine completes one power cycle in four piston movements. Thus, compression ratio is a key factor in determining energy efficiency. Higher compression ratios typically leads to higher efficiency, but also higher pressure and temperature. So now, let's discuss the relationship between the compression ratio and the work done in the engine. So heat recoveries in ICs. So as you all know, some amount of heat is lost due to the combustion processes. So some energy lost in an IC can be recovered using systems like turbochargers or waste heat recovery systems. So this is a typical example of how a turbocharger works. So this is in real life, and this is like a diagrammatic form of a turbocharger. So it has the intake manifold, the throttle body, the compressor, the shaft, the turbine, the exhaust manifold, air intake, waste gate, and exhaust pipe. So discussing turbocharging, that's a method to improve efficiency by recovering energy from exhaust gases to boost engine power. Challenges in IC efficiency. Despite improvements in the efficiency of ICs, remains a challenge due to inherent losses like friction, heat dissipation, and incomplete combustion. Recent advances in IC efficiency, so new materials, hybrid technologies, and advanced combustion methods are being developed to increase the thermal efficiency of ICs. So mention direct injection, variable valve timing, and turbocharging and all that. Now, real-world application of the first law in IC. So in real-world engines, the first law of thermodynamics is critical in optimizing performance, reducing fuel combustion, and improving emissions. Challenges in IC efficiency. So despite advancements, improving the efficiency of IC remains a challenge due to inherent losses like friction, as I said earlier in my previous slide, heat dissipation, and incomplete combustion. So summary and key takeaways. So the first law of thermodynamics governs the energy conversion processes in internal combustion engines, explaining how energy is transferred and transformed. So the key points: the role of heat input and work output, then the concept of efficiency and energy losses and ways to improve efficiency. Thank you.